Hello everyone, I'm William and I'll be walking you through the setup of our latest NLP paper on tokenization and surrounding formalisms. First of all, what's tokenization and why do we need it? There are many word types and languages, and most NLP models require to have a predefined vocabulary for which we have, for example, different embeddings. If you took each word as a separate unit, then we would have a vocabulary size of maybe 1 million, which is problematic out of multiple reasons. On the other hand, if we separated each word as a sequence of characters, then we would get very long sequences, and the semantic embeddings for each unit, that is characters, would be meaningless. The solution is maybe somewhere in between, where we split words into some chunks. But there are many possible ways to do this tokenization, and which one is the best one? The best tokenization is such that it maximizes the performance of some downstream NLP model. So we can generate multiple tokenizations, then train a model on top of this tokenization, and take a look at the performance. There is an issue with this. For example, in the context of machine translation, the tokenization takes just a few minutes, as well as the evaluation using automatic metrics. However, training the machine translation model from scratch takes at least a week on a single GPU. Using this evaluation method of tokenizations quickly becomes unsustainable. Now the question becomes, how can we select the best tokenization without actually having to train the whole model? The first option is to just use by-pair encoding with a vocabulary size of 32,000 tokens. This will cover most application cases. However, if you are interested more in principled understanding of tokenization, we have to go deeper. We can, for example, look at the token distribution and look at its tail and look if there are any tokens that occur very infrequently. If they do, we can say that this is not a good tokenization because the models won't be able to learn the correct meaning of those low-frequency tokens. However, this is a very hand-wavy evaluation approach. If you look at these two different distributions, which one is better? One way to look at it is that it's the one on the right, and the reason is that the token frequencies are more balanced. So now we are looking for some metric of distribution that tells us how uniform it is. And entropy turns out to be a very good tool because it measures how spread out the distribution is. In the paper, we use more complex measures such as efficiency and Renyi entropy, which also tell us something more about the nature of tokenization. Let's compare this predictive measure with the sequence length, that is, how many tokens on average are in the tokenized segments. In these graphs, each point is a separate tokenization and an empty system. The y-axis is the performance as measured by Blair, and the x-axis is the predictor. Clearly, the Renyi entropy is much better at performance prediction than the sequence length. In our paper, we develop proofs which justify and explain why Renyi efficiency is a good predictor and compare it to many others. We also go into much more detail than the space of this video allows. Thanks for listening and let me know if you have any questions. Also take a look at our other paper which deals with specific tokenization approach, by-pair encoding.